AP Physics C, Electricity and Magnetism. And we are reviewing you for the AP test. Today, we are going to go over electric flux and Gauss's law. And if you have not watched kind of our first couple of videos with charge and Coulomb's law and finding electric field, it might be a good idea to watch those first. But tonight, we are going to do Gauss's law. My name is Krista Gonzalez-Vega, and I'm with my friend Roger.
Hello, my name is Roger Siegel, and I'm coming to you from Sarasota, Florida.
All right, so what we're going to go through today is we are going to state and apply the general definition of electric flux. We are going to calculate what that electric flux is through an arbitrary area. We're going to calculate the flux through a rectangular area when the electric field is perpendicular. And then I highlighted this one. This is kind of a big one here. We're going to qualitatively apply Gauss's law to a system of charges or charged region to determine characteristics of the electric field, flux, or charge contained in the system. And we're going to state and use Gauss's law in integral form to derive unknown electric fields for planar, spherical, and cylindrical symmetry charge distributions. So it sounds like a lot, but really it all kind of relates. So the first thing we're going to talk about is what is electric flux? And so not even necessarily electric flux, but what is any flux? So a flux is a flow of some quantity through a surface. So I like to kind of use the analogy first of light. So if we look at the picture here, we can see this light streaming in, and you can see those light rays streaming in. And so that amount of light that is flowing into this church is the flux of the light. And so we can change the amount of flux by changing those windows. So what could you do to change the amount of light? Let's say I want to increase that flux of the light coming through. What could we do? There's a couple of different things we could do. Think about the time of day. In the morning, like maybe let's say this is afternoon. So in the morning, would you get the same amount of light streaming through the windows as in the afternoon? No, that angle that light is hitting at affects how much light gets through. What about the size of the window? Would that affect the amount of light that gets through? Yes, the bigger the window, the more light that's going to stream through. And so we can relate that amount of flux to both kind of the surface area of the window, the angle at which the light is hitting, and also the intensity of the light that's coming through. So let's look at some examples down on the bottom of the page here. And we have sunlight shining in one side of the building and out the other on that lower left. And if we look at that flux, the net flux is that total in and out light, right? So if we have light coming in and light going out, like we do here, we have no net flux because no light is staying in, or we don't have a net flux that's going out. And so we say generally that positive flux is when you have a quantity that's flowing out, right? So if we had light inside the building that's flowing out, like the middle picture, that would be a net positive flux. But the first picture, we have just as many light rays going into our building as going out, right? Let's imagine this is a glass greenhouse. Just as much as coming in that is going out. And so that would be, let me get my pen out here, that would be zero net flux because there's the same amount going in as there is coming out. In the middle, we have light that is originating in the inside. And so the light rays are only leaving the building. There is nothing coming in. So that would be a positive flux. And then if we combine the two and we have light on the inside coming out, because that light bulb is on, but we also have sunlight coming through the building. Well, if we look at the sunlight, again, that's like the first one, that's zero, but the light inside has a positive, that gives us still an overall positive flux. There'd still be there'd be more light leaving that building than coming in. Okay, so we can use that analogy now to talk about how we can use this for charges. So I have a couple of different surface areas here, right? So it's the flux again is the amount of, here we'll say field lines that are going through our surface that we choose. So let's just kind of practice, is there a net inward or outward or any kind of net flux on our surfaces? So let's take a look at this one here. So I draw this surface area. And if we look at this surface area, let's look at the electric field lines. Well, I've got field lines going into this surface. So that tells me I would want to have a negative flux. But then I also have those same lines going out through my surface. And everywhere on that surface, any field line that's going in is also going out. So that means here we have no flux. Okay, but if I look at the surface area that's surrounding this positive charge in the center here, well, if we look at the field lines, we have field lines that are, and this is my whole surface, right? This whole thing is my surface. So there are field lines only leaving the surface everywhere around. So that would give us a positive electric flux. Okay, you guys starting to get with me here? So let's look at these three down here. I'm going to give you a minute for these three surfaces. You tell me positive flux, negative flux, or no flux. So we got those two, and then we've got the big one all the way on the outside. Okay, so take a second. This would be number 1, number 2, number 3. Positive, negative, or 0. Okay, what about number 1, the one on the left? Well, we have field lines only going in to our surface here. So that, for number 1, would give us a negative flux. Sorry, positive flux going, or yeah, negative flux going out. What about with the positive charge here? We have only field lines going out. Well, that would give us a net positive flux. And if we enclose both those charges, well, we have field lines going in and we have field lines going out, and we have just as many going out. As you can see, they kind of loop back around and come back in. So that third one would be 0. Okay, so let's look at what this really means then as far as like putting a quantitative amount to it. So how could we actually calculate what this flux is? So that amount of flux, as you can see, depends on the electric field lines, but depends on that surface too. So if we imagine this one charge in the center here, and I'm going to draw an imaginary surface around it, right? Or if we think of like a balloon with a point charge inside of a balloon, if I break the surface up into tiny, tiny little pieces, and I can do lots and lots of them, right? So we have a tiny little differential surface area on our surface. And if we think of what's normal to that surface, then we can look at the electric field lines going through each of these surfaces, right? And since it's like a 3-dimensional surface, they're going to be coming out in all different directions. Some will be coming right out at different sides. And so we can find, well, what would be the flux of just this one, right? Well, since it's not the whole entire surface, we're looking at just a little piece of the whole surface, we can say, well, that's a small differential part of the flux. And so we can look at the electric field going through that one surface area times our tiny little surface area. So that would be the electric flux through just that one tiny little differential surface area. And if I want to know what the entire flux is over the whole surface, what do we have to do? Well, we have to add up all of those tiny little fluxes. And so we end up with that the net flux across our whole surface would be equal to the integral of E dot dA. And that's for any surface, right? You get to pick the shape of your surface. And it's important to remember, like when we talk about these surfaces, we call them these Gaussian surfaces. It's not a real physical thing. It's just a region of space that we're enclosing around our charge that we want to determine the electric field of. So sometimes we'll have spheres. I could have a rectangular prism here and look at the flux through this one. We have cylinders as well. Those are kind of our 3 common shapes that we use, are the sphere, the rectangular prism, and the cylinder. So if we look at this rectangular prism down here, we want to look at which surfaces have flux, because sometimes when we draw our Gaussian surface, there may be some surfaces that have no flux. Because if we look at it, this here, in order for there to actually be flux, the field can't be running parallel to the surface. If my sun is coming straight down on top of my house, it's not going to enter the window, right? So there would be no flux there. There has to at least be some angle. So we're looking at the component of the electric field that is normal to that surface area. So if we look at these front sides of my rectangular prism, well, those that surface area is running parallel to the electric field. So there would be no flux on those front sides. Same thing with the top side, with the back side. But where there would be flux, we can look at the two end sides here. But we have field lines going in one side and coming out the other. And if this field were the same, or it was a uniform electric field, then there would still be no flux here. Now, if the field was different, then there would be. But if we're saying this is a uniform field, still no electric flux through that surface. So that's one way we can find the electric flux, is that we can relate the electric field through the surface area. Okay, but that electric flux also depends on the amount of charge that's enclosed in our surface, right? So if I go back and we look at these ones again, you could see, well, what's inside that surface? Well, here we have a positive charge inside. That's what's affecting also the flux. So there are two ways we can find the electric flux. We can use that integral of E dot dA, which when we actually draw our now Gaussian surface, we have to integrate across the whole surface. That's going to be a closed integral. So we could use that side is the electric flux, but also the right side is the electric flux. So we could also find it by finding the charge enclosed divided by epsilon naught. And what epsilon naught is the vacuum permittivity constant. That's going to be equal to 8.85 times 10 to the negative 12 coulombs squared per Newton meter. Sorry. But it's also the same thing. We can relate it with K, because what you know, you've heard of K before, right? That Coulomb's law constant. K is equal to 1 over 4 pi epsilon naught. And so we can also relate epsilon naught to K. So the rules for being able to use Gauss's law. So this is Gauss's law. And we can use this to find the electric field. We found the electric field for the point charge, and we're going to derive it here in a second with Gauss's law. But Gauss's law is kind of our shortcut, or our easy way to find electric field around charges. But there's some rules that we have to follow in order to use it, because we can't use it all of the time. The first thing is that your Gaussian surface, right, that region of space that you choose around your charge, has to have the same shape as your charge distribution, right? So if I have a point charge and we say our point charge is a nice sphere, then my Gaussian surface that I choose to enclose my charge also has to be a sphere. I cannot use a square. The reason for that is because in order for this to be true, in order for us to be able to do this integral, we want the electric field to be constant everywhere on my surface. Well, and that gets us with the square, because if we know that electric field relates to the distance away from the charge, the corner of a square or a cube is further away than, say, the midpoint on that cube. So the electric field wouldn't be the same everywhere. And the last thing is the electric field must be tangent or normal to the surface. We don't want to be dealing with angles and things like that. So we choose that symmetry that's the same as our charge, so it becomes easy for us to solve for the electric field. Even though it's an integral, if you are choosing your Gaussian surface right and applying Gauss's law right, you will never have to do any calculus. Sometimes maybe for the charge, but not for actually Gauss's law. So let's use an example here. And I'm going to really quick try to switch over and see if I can draw on my iPad, because that is easier than trying to draw here on the PowerPoint. So I want you to read this. I've got a point charge, positive Q. And it is, we want to know what is the electric field at some distance r away from the point charge. So we derive, well, we didn't derive it, but we got an equation yesterday for the electric field due to a point charge. So we are going to see how we got that. All right, so I want to switch over here because I've got it working now. There we go. So we have our point charge here. First thing we have to do, and here's our steps on how we apply Gauss's law, and it's the same all the time. Every time you're working a problem with Gauss's law, you solve it the same way. The first thing you want to look at is, what is your charge? What is the shape of your charge? Because then that's what you're going to use to choose what your Gaussian surface is. Remember, your Gaussian surface is that region of space that we're going to enclose our charge in. Because we want to know, let's just say that I want to know what the we go. What the electric field is at this point here. Which my screen is frozen, so I'm probably gonna have to switch back over. Gotta love technology. All right, I'm gonna switch back over because that's taking way too long to pop up. So let's go back to the PowerPoint. So let's say right here, I wanna know what the electric field is. So the first thing we need to do is we need to determine what Gaussian surface we're going to use. Well, what shape is our charge? It's a sphere. So I'm going to draw a Gaussian surface. It is a nice sphere surrounding that charge. Okay, the second thing we're going to do is we're going to write Gauss's law. So we know Gauss's law is the integral, closed surface integral of E dot dA that equals Q enclosed over epsilon naught. So then we address, well, if we look at our surface, right, and we integrate all the way across, well, what will the integral of that, all those dAs always be? That's going to be the surface area of your Gaussian surface, always. So if I look at this, I am equal distance away from my point at every place. So that means my electric field is going to be the same everywhere on my surface. So now E is a constant, right? That's the other reason why I always pick that symmetry. E should always be a constant. It should never be different on different points on your Gaussian surface. So really this just becomes E times the area. What is the surface area of a sphere? Well, it's 4 pi r squared. So if I want to know for any r away, we are always going to put that little r, unless you're looking for a specific point. If you're just looking for an equation for or a function of the electric field for that radius, then we're always going to leave this left side of Gauss's little r. So that equals, okay, well, our next step is then to address what part is the Q enclosed. Well, here it's easy. What amount of charge is actually inside your Gaussian surface that you draw? And here, what's inside? Well, it's Q over my epsilon naught. So if I rearrange for E, E becomes Q over 4 pi epsilon naught r squared. And remember, we know that 1 over 4 pi epsilon naught is K. I could leave it as this, or I can put it in terms of K and say that it's KQ over r squared. Ah, that looks familiar. That's the equation we used last night. Okay, so that's for our point charge. Let's now look at if we have a conductor. Okay, so I put in parentheses here nice and big. Always remember where the charge exists. So let's see if we can set up here our Gauss's law equation. Let's look at, let's look at when we are at a distance r of less than big R, right? So we're inside. So again, I'm going to draw my Gaussian surface. You can draw it any size. It doesn't matter if you draw a small circle, as long as your Gaussian surface is going to be less than R. Okay, so we're going to write it out. We know that Gauss's law, integral of E dot dA equals Q enclosed over epsilon naught. Okay, we're going to address the two things always. What is the surface area of my Gaussian surface? And what is my Q enclosed? Well, it's still a sphere. We're still dealing with a sphere here. So we've got E equals, or E times my surface area, which is 4 pi r squared equals, what is the Q that I've enclosed here? Well, here's where we have to look and always pay attention whether you're dealing with a conductor or an insulator. Because remember, in an insulator, the charge can be evenly distributed or unevenly distributed, but it's throughout the whole surface, throughout the whole material. But on a conductor, where did we say the charge always is last night? It's always on the surface. Inside surface, outside surface, always on the surface. So that positive charge would be distributed around the surface of that. So what charge is on the inside of the conductor always? Nothing. There's never charge on that inside space of that conductor. Therefore, what will our electric field always be on the inside of the conductor? 0. Okay, and then the next one, if R is greater than R. So I'm going to redraw that Gaussian surface. I'm going to change colors. I want you to redraw your Gaussian surface. See if you can solve for what that electric field is at an R, anything greater than big R, the radius of that conductor. Okay, first thing, we draw our Gaussian surface. Again, it doesn't matter if you're drawing it way outside or just outside. We always want to follow our symmetry. So it's still a sphere. It's just now a bigger sphere that's enclosing the whole conductor. Okay, so we still go back to Gauss. And it gets repetitive, but you still always want to write it out. You always want to use your full steps here, right? So now our surface area is still the same. So E times 4 pi r squared. Even though we're outside, it is still little r, because I want to know for any r, what could I find the field? So this left side could be for any r. What Q have I now enclosed? Well, now what's all inside my surface? Everything. So now this becomes Q over epsilon naught. So again, we're left with, that E is equal to Q over 4 pi epsilon naught r squared again, or KQ over r squared. Okay, and we've got to be able to draw this, right? So we have to be able to say, well, what would this look like on a graph of the electric field? And I'm going to even put in here that at this location, it is big R. We're right out here at the edge of that conductor. So the only thing you have to do is you have to look at your relationship. What relationship does E have to R in our equation when we were looking at it for less than R? Well, the E was 0 the whole time, right? And then the minute we jump out here, let's look at the relationship between E and R. Well, R is squared and it's on the bottom, so it's an inverse square relationship. So when we get outside here, that electric field's going to jump way up. It's going to be the biggest it's going to be. But then as we go further and further out, that electric field is decreasing exponentially by that 1 over r squared relationship. Okay, so we always want to be thinking about what is that charge enclosed, what surface area, what Gaussian surface am I going to draw? Okay, let's look at one more here. So now we're going to look at an insulator. Okay, our insulator though has a uniform charge density. So I'm going to go through these different densities with you because we're going to have to know what our different charge densities are. We can have 3 different types of charge density. I can have the what we call linear charge density. So that would be if I had like a really, really thin object or thin line, and that's equal to the charge per length. That's lambda. We can have sigma, which is the area charge density, and sigma is equal to the charge per area, right? The area charge density is the amount of charge per area. And then we can also have rho when we're talking about our 3D objects here, and rho is equal to our charge per volume. So those are 3 different kinds of charge densities we can have. So we're told here not always what the total charge is. You may be told that it just has uniform charge density rho, or you may be told what the total charge is. You have to be able to kind of relate them both. And so if I know here that the total charge is Q and that it's uniform charge density, then we want to look at what is the electric field at less than R and greater than R. So if we start than less than R, we're going to draw our Gaussian surface. What shape are we still dealing with, guys? It's still a sphere. So I'm still going to draw my nice sphere Gaussian surface. So we're going to write down Gauss's law. And then again, we're going to plug in for both sides. Where it's going to get complicated here is with that Q enclosed, right? You guys see that. So it's still a sphere. The left side, still the same. 4 pi little r squared, because I want it for any r from the center all the way out to here. Okay, but now we have to look at how am I going to get how much charge is in just this part of my Gaussian surface. Well, it comes back to, I know that just like if I take a ruler and I break it in half, the density of one half of the ruler is the same as the density of the whole ruler. So I can use that here too, because I know that the charge density of the whole insulator here is equal to the charge density of whatever I'm enclosing. That density is the same. And so then I can say, well, that means that the charge of the whole thing, which is Q, over the volume of the whole thing, well, it's a sphere, so the volume of the sphere is 4/3 pi r cubed, but this is the whole thing. So here we are going to use what R? Big R. That's got to equal the charge that I'm enclosing, so Q enclosed, over the volume of just my enclosed part, which is 4/3 pi little r cubed. Okay, now we can just solve for Q enclosed. My 4/3 pi is going to cancel. And so my Q enclosed is just going to be equal to the total charge Q times my little r cubed over big R cubed. And so that's what I'm plugging in for my Q enclosed here. So I get big Q times little r cubed over, I still have my epsilon naught, times big R cubed. Okay, if we solve here, I'm going to divide by my 4 pi r squared, so I can cancel out the cubed with the r squared here. And so I get that E is equal to Q over 4 pi epsilon naught, times R times big R cubed. Okay, so let's put that on our graph here. So anywhere between 0 and R, what relationship does the electric field have to the radius? That would be little r, right? Well, where's little r? It's on the top and it's by itself. We saw this when we were looking at magnetic fields. It's going to have a linear relationship until we get to that outside. It's a direct relationship and increases. Okay, let's look then at when we are r bigger than r. So let's see if you can set that up. It probably should be pretty easy at this point on what it is. But if we draw our Gaussian surface that's bigger, which mine is not super circular, I apologize. And we set up our equation, still a sphere. So it's still 4 pi r squared. But what charge are we now enclosing? We're now enclosing everything. It's still little r on the left, as you notice, because we want it for any r. It's not a specific r that we want it at. So that's just Q now over epsilon naught. And what do we get again? We get that E is equal to Q over 4 pi epsilon naught r squared. So we go back to that inverse square relationship. So from there on, curving back off. Okay, so those are kind of our sphere shapes. Roger's going to show us a couple of other charge distributions.
Yes, thanks, Kristen. Well, let's do, we've just done a sphere. So let's go ahead and I'll share my screen and let's do a line of charge. All right, so I want to, let's see, this guy is actually, hold on a second. Okay. Great. So let me come back here. All right. So Kristen alluded to this earlier. If we have a line of charge, okay, now I don't mean a wire where the charges are moving. I mean, I've got some plastic, something that's an insulator, and I'm embedded charges in there so that my charges have this density lambda, and the units for lambda are coulombs per meter. And that's why it's called a linear density. All right. Now, if we want to find out what the electric field is a certain distance away from this, what we're going to do is we're going to use Gauss's law, and we're going to create a Gaussian surface. So Gauss's law is E dot dA is equal to Q enclosed over epsilon naught. Now, what kind of Gaussian surface do we choose? Well, with a point charge, we chose a sphere, spherical Gaussian surface, or with a spherical charge, we chose a spherical Gaussian surface, because at every point on that Gaussian surface, the electric field was exactly parallel to the area vector. So let me show you looking on. This is my looking from the edge here. And so if I look at this, my electric field lines are going straight out, okay, like this. And so what kind of Gaussian surface would I want to create such that my area vectors are always parallel to my E field vectors? And I'm going to create, for these sides, I'm going to create a cylinder. And why a cylinder? Well, because and the body of the cylinder, the E field and the E vector and the A vector are parallel. And so that means that E dot dA, and that's a dot product, that's going to be, you know, that's E dA times the cosine of the angle between them. And so the cosine is 0, and so that works. Now on the edge here, the A vector is, again, the area vector is always perpendicular to the surface, but the E vector, again, is radially outward. These two are perpendicular, and the cosine of 90 degrees is 0, which means there is no flux through either of these faces. So if I'm going to draw a net diagram of my cylinder, okay, we know that this is R, this is R, and through each of these sides, the flux electric is 0. Here, the flux electric is 0 for these, because again, the area vector and the E field vector are perpendicular. And here, the flux is the integral of B dot dA, and that's equal to the Q enclosed over epsilon naught. Now, well, the B field is, I'm sorry, I said the B field. I'm in the wrong unit, ladies and gentlemen. That is another formula. This is E dot dA. Sorry about that. And so for this E field, we want to figure out what this is. And so we're saying, again, everywhere on here, the E field is parallel to dA. And so this just is uniform. This just becomes E. The area of this part of a cylinder, well, this is, I didn't draw this here, but the length of the cylinder from here to here is L. And this part of the cylinder, you may remember from earlier, is 2 pi r. It is the circumference of this circle. So this middle part, when I integrate the dA, I get 2 pi r, and over here I get the Q enclosed over epsilon naught. Now, just like in the previous problem, the Q enclosed is the most challenging here. What is the Q enclosed? Well, remember that my charge density is lambda coulombs per meter times however many meters gives me the charge. That's going to be lambda times L. And you know what I forgot here, ladies and gentlemen? I forgot that the area is 2 pi r times L. So we come down here, the L's cancel. And so E is equal to lambda over 2 pi r L epsilon naught. And that is our, our E field, a distance r away from a long line of conductor. All right, let's do one more, and then we're going to send it back to Frisco, Texas. And that is the plane of the charge. Maybe we'll do more than one, we'll see. Now, again, when you're choosing your Gaussian surface, the reason you're choosing it is you're choosing a specific surface such that either the area vector and the E field vectors are parallel or perpendicular. Now, a lot of times this is taught again by using a cylinder around this, and you can see here it's kind of the opposite case. So let's take a look at this and see what we have. We've got this cylinder, and now in the previous problem, okay, the E field was parallel at the ends to the A field, and so the ends contributed nothing to the flux. We have just the opposite here. Notice that the A vector and the E vector here are perpendicular. That means that on our net diagram here, the flux electric is 0 because E is perpendicular to dA. Everywhere along here, everywhere on the body of the cylinder, E is perpendicular to DE field. However, at the caps, notice E is parallel. And so what we have here is we have pi r squared here, and we have pi r squared here. And so when we add up, when we do Gauss's law, E dot dA, okay, and we sum that up, Q enclosed over epsilon naught. Now let's talk about, well, let's do this left side and then we'll come back and talk about the right side. Now here we have, again, the electric field is uniform. The whole point of doing Gauss's law is to not have to integrate. And so we're going to pull that out. And now what is the area when I integrate over this whole thing where I don't get 0 flux? And that is pi r squared and pi r squared, and I've got 2 of them. So there's 2 pi r squares, and that's equal to the charge enclosed over epsilon naught. Now, let's look at this. I failed to drill down here for a minute, so I want to come up here. It says we've got an infinitely charged plate. It's very, very big, and the area density is sigma. Now, that is different than lambda, different than rho. Remember, lambda is coulombs per meter. Sigma is coulombs per meter square. It is the area density. And so I've got this very, very thin plate with sigma coulombs per meter. And so I'm going to go ahead and come up here. And what do we have? We have the charge enclosed. And so that's sigma. And the charge enclosed, if we look back down here, how much charge have I got? Well, I've got a little cookie cutter. Look, I've cut out this much charge. And so how much is there? Well, that's pi r squared times sigma. The area times the density will give me the charge that is enclosed. And so that's going to be, I'll say E times 2 pi times pi r squared, those are the 2 end caps, is equal to pi r squared times sigma over epsilon naught. And so this becomes E, look at this, the pi's cancel, the r squared cancel, and E is equal to sigma over 2 epsilon naught. Now, I just want to pause for a minute because this is important. What is missing from this formula? What are we saying that the E field depends on? Well, really, there's only one thing, and that is the density. And more importantly, more crazily, what does it not depend on? Well, strangely enough, the E field does not depend on the distance I am away from my plate. The math gives it, and there's other ways to prove it, but it's something we can certainly show. Also, it's on MIT's Lewis Lewin physics. It's very well demonstrated as well. Now, we've got some more to do, but we're going to throw it back to Frisco. Are you ready back there for me, Kristen? Because I want to make sure we get these kids out at a decent time.
Yeah, sure. I think we should probably do the conceptual part of the question, right?
Okay.
Just scroll through. Let me show you what I'm talking about.
Yeah, let me go ahead and release my screen.
And I'm back in business with my Apple Pencil, so my handwriting is going to be much better than my clicks of my mouse. I apologize again for that. So what we're going to look at is a free response question. We're going to kind of skip the first parts of this because it's what we were deriving earlier with me, that we have a non-conducting sphere and we're looking at what is the electric field at greater than A. We've already done that. I think we're good on that. But what I want to look at is, if we scroll down here, is this conceptual part, because that's what we want to practice the most. If we have here 4 point charges, Q1, Q2, 3, and 4 in the plane of the page here, and we want to imagine this three-dimensional closed surface, right? This kind of globby 3D surface that is shown in our diagram. And we want to know which of these charges is going to contribute to the net electric flux and which is going to contribute to the net electric field, and are they the same or not, and why? So I'll give you just a minute here to think about that. Which of the charges are going to contribute to the net electric flux, and which ones are going to contribute to the electric field at point P right here that lies on that surface? Okay, so which one are going to contribute to the net electric flux through the surface? Or remember, what is that flux equal? The electric flux is equal to either that integral of E dot dA or equal to Q enclosed over epsilon naught. So one thing we can look at is that the flux only depends on the amount of charge enclosed. So which ones do we care about? We care about the ones that are enclosed, which are only Q2 and Q3. Because the other ones, our field lines are going to go in one side of the surface and out the other, right? If we look at Q1, let's say it's a positive charge. We know field lines go away from positive, so it's going to go, well, it's going in one side of the surface, out the other. That's not contributing to the net flux. So the only ones that will are Q2 and Q3. But which ones will contribute to the electric field at point P? Well, even though Q1 and Q4 are not within our surface, they don't contribute to the flux, but they will contribute to the overall electric field. Because if this is positive charge again, well, at point P, there would be an electric field due to that charge kind of going off at that angle there. So the answer is all of the charges will contribute to the electric field at point P, which is why if this would not be a Gaussian surface that we could use to find it, right? These are point charges. We wouldn't be able to draw a Gaussian surface that had symmetry, where the field was the same everywhere, that we could apply Gauss's law to. Okay, so why are they different? Well, they're different because really we're not talking about the same quantities, are we? Flux is different than the electric field. Flux depends on charge enclosed. While the electric field depends on all the charges in that space around it. All right, so kind of defining what those two things are and why they are different quantities. Okay, if the net charge enclosed by a surface is 0, does this mean that the field is 0 at all points on the surface? So what that means is, if we said that this is, say, a positive 1 nanocoulomb and this is a negative 1 nanocoulomb, well, what we're saying is that charge enclosed is 0, that we have a net 0 charge enclosed. Does that mean that our electric field has to be 0 everywhere on this Gaussian surface? What do you guys think? Okay. Well, the answer is no, it doesn't have to, because the electric field is not the same everywhere, right? If we look at here, if I look at this point, well, the electric field at this point, which is due to all of these charges, is not going to be the same as the electric field on this point on the surface. So this goes back to, I mean, if you want to, some people may want to say, well, because Gauss's law is the integral of E dot dA is Q enclosed over epsilon naught. If the Q enclosed is 0, that means the field has to be 0. Well, that's only if you can use Gauss's law. And we can't use Gauss's law here because our field is not the same everywhere on that surface. So no, it's not true. And so some things that we could say there is the field is not the same everywhere. Okay. We also could have like an electric dipole on there, right? But really it still all goes back to the electric field is not the same on all points on that surface. And then there was one more too that I didn't put on here that I want to ask you before we go. And that is the reverse true, right? So if the electric field is the same everywhere on our surface, does that mean that there has to be no net charge enclosed? So if the field is 0, let's go over here. So if the electric field is 0 everywhere, is the Q enclosed 0? And that is true. The only way that we could get that 0 electric field there is if our Q enclosed is 0 everywhere. Okay, so that is Gauss's law for tonight. Hopefully, conceptually, you can explain what surface you would choose. I can see that being asked on exam this year, absolutely, is given a charge distribution or shape, what Gaussian surface would you choose? Looking at what charges are contributing to flux or contributing to field, kind of like that end question here that we dealt with. And understanding the concepts behind it and not just kind of the derivations of all of the E fields that we derived. Is it important to be able to do that? Absolutely, because math can still explain concepts, but understanding that basis of what is Gauss's law, what kind of surface would you choose is really going to be important for the exam. Roger, anything you want to add in? You want to unmute yourself?
Thank you. I just want to again unmute myself and say thanks for working so hard. We really, we know you guys are working hard, getting ready for the exam on the 11th. And we hope that you keep joining us every evening and we can do this together.
Okay. We will see you tomorrow.